So in a previous module, we talked about first order conditions for a minimum, and now we're going to talk about second order. First, let's try to streamline our use of Taylor series. So you might remember this is our basic second order Taylor polynomial. I'm going to keep saying Taylor series. Really what I mean is Taylor polynomials. We're just doing a few terms rather than the infinite series. So you probably, when you were first learning Taylor's polynomials, didn't like writing x minus x0 or x minus c or something over and over again. So let's try to streamline that. We'll define h to be x minus x0, and then you think about, you could, based on this, what can you say that x is? Something involving h and x0 maybe. So go ahead and rewrite this Taylor polynomial using this kind of streamlining. Okay, so let's see what we have there. So x is x0 plus h, which is like initial point plus a movement away from the initial point. And so now we, instead of x minus x0, we just have times the distance moved and times the square of the distance moved. So this is called the incremental form of the Taylor approximation. And you might get the feeling that it's like Maclaurin series, because there we just had an x here and an x squared, and it basically is, but with our base is at x0 instead of at 0 like it is for Maclaurin. So it's a nice kind of happy medium between Taylor and Maclaurin. So that's the single-dimensional version. Let's think about the multi-dimensional version. Go ahead and write down the multi-dimensional Taylor polynomial, order 2, and then write an incremental form of it. Pause the video while you do all that. Okay, welcome back. So here's a multidimensional version of the Taylor polynomial in incremental form. So now that we have vectors and stuff going on, it's a lot nicer to just have that vector h there instead of x minus x0. Let's talk about some Taylor polynomial shapes. What do Taylor polynomials look like when we break them into their component pieces? So let's first just look at a Calc 2 view. So here's our constant term and our first order term and our second order term. So go ahead and sketch what each of those looks at a point that's probably not optimal. And then once we do that, then we'll come back and try sketching them at optimality. So pause the video while you sketch what each of those terms looks like in the non-optimal case. And here we go. The constant term could just be any constant, y equals a constant. The linear term could have a positive slope, could have a negative slope. It'll go through the origin though, because its intercept is just this term is 0 because the intercept is over here. And then the second order term could be a parabola like this or a parabola like that. Again, going through the origin because the intercept is over in this term. So now based on that, try sketching what must be true at optimality. So pause the video while you do that. Well, here's what it looks like. The linear term now has to be perfectly flat because the derivative has to be 0 at optimality. And to be at a minimum, we need to have a parabola that's like this and not like that one there. So that's what this looks like in Calc 2 frame of mind when we just have a single x variable. So now let's go think about it in the multidimensional case. So now let's be clear about our axes. H is a vector. Here's the first component of h going this way. Here's the second component of h kind of coming out of the screen or into the screen. And then the objective function value is the vertical axis here. So go ahead and sketch what each term looks like at non-optimality. So we're thinking in 3 dimensions here, and I mean the same axis labeling for all of these graphs. All right, so let's go see what we've got sketched here. So the constant part is just a perfectly flat plane. The linear term could be a tilted plane this way or tilted plane that way or this way or that way through the origin. And then the quadratic term or second order term is kind of interesting. It could be a bowl like this, which could be squished this way or squished that way. It could be a bowl like this, which could be squished this way or that way. Or it could be more of a mixed term that's like a hyperbolic paraboloid or a saddle, where it's kind of got this curvature going left to right and this curvature going front to back. So it could be any of those. And then what will these look like at optimality? Think about that. Pause the video. So here's how I've drawn it at optimality. So again, the constant term just could be any constant, flat plane. The first order term, the gradient has to be the 0 vector, and so this whole term will be 0, and so you'll just have a flat plane through the origin. And then for the second order term, for us to be at a minimum, we can't have the second order term letting us go downward at all. So it can't be this green downward bowl, it can't be this hyperbolic paraboloid beautifully sketched in black. It has to be something that is like this. Again, it doesn't have to be perfectly round, it could be squished this way or squished that way. So that's how we're visualizing the Taylor polynomial at optimality. It's kind of a sum of these things. First order condition is that the gradient has to be 0. What can we say about the second order thing? So that's the big question. We need this term to never be negative, right? Because if it can be negative, then we could decrease the objective function value by moving in one direction or the other. So, and this term is basically h times the Hessian times h. So we need our vector h, our incremental direction vector, times of Hessian times h to never be negative. And that would give us kind of an upward facing bowl. And so our x0 vector would be our local minimum. So let's think about that some more. We will have a definition that says if that h times some square matrix times h is strictly positive, then we'll say that the Q matrix is positive definite. And if it's usually positive but sometimes 0, then we'll say that's positive semi-definite. Notice we're not allowing h equals 0 here, because then we would just always get 0. It's too boring. And if the product is always negative or 0, we'll call that negative semi-definite. Purely negative, we'll call it negative definite. And if sometimes the answer is positive, sometimes it's negative, then we'll call Q indefinite. And this is true for any square matrix, but not necessarily a Hessian, but we'll usually be using it on the Hessian. Usually we'll only apply it to symmetric matrices too. So using this new idea that we're at a minimum here when this shape is like that, go ahead and write down some what you would conjecture is the second order necessary conditions and second order sufficient conditions for minimizing, and you can assume that we're at a first order necessary condition kind of point, and we'll look at the answer in the next video.